All right, so now we're in the chapter 2, and lesson 2.1 talks about the nature of matter. So, what are you made of? Just as building blocks are made of bricks, steel, and wood, all forms of life are made from chemical compounds. So, in the key questions we're going to tackle here in this is the three subatomic particles. Subatomic means smaller. How are all isotopes of an element similar? In what ways does a compound differ from its component elements? And what are the main types of chemical bonds? So let's start with our first key question here. What three subatomic particles make up an atom? So all living things are made from chemical compounds. And when we're looking at chemical compounds, just how these atoms form together. So when we're looking at an atom, the atom is the basic unit of matter. So all of matter, everything that makes up the universe around us are made of these atoms. And the particles that make up an atom are protons, which are the positive molecule found in the nucleus, neutrons, which is the neutral molecule found in the nucleus, and then electrons, which are the negative particle flying around the nucleus that are responsible for bonding. So again, protons, neutrons, and electrons are our three subatomic particles. So let's start with protons and neutrons. Now, protons and neutrons are found inside of the nucleus, and the nucleus is the center of an atom. So the center of the atom contains protons and neutrons. So again, these two molecules are found at the center, and they have about the same mass. So protons and neutrons are a much more massive object. So if we look at this and we look at the charge, remember protons have a positive charge. Usually we indicate that as a +1, whereas neutrons have no charge or neutral. They have a zero charge, right? Now, when we kind of think about these, again, neutrons are neutral. But when we're looking at these in terms of mass, a proton and a neutron have the same mass, 1 AMU. So what an AMU is an atomic mass unit. So when we're looking at the mass on the periodic table, the number of protons and neutrons designates what that number is. So these are bonded together by strong atomic forces. And these strong atomic forces hold the protons and neutrons into this nucleus structure. So the other subatomic particle we have are electrons, and electrons is a negative charged particle. So again, they are in constant motion around the nucleus. So electrons are moving, okay, and they are moving, they are in motion around the nucleus. Now, the electrons are the ones that are responsible for bonding. So electrons, they are arranged in a series of orbitals called shells. And these shells, especially the outer shells, are responsible for all of its chemical properties. So in an electron or in an atom, in the first shell, it can hold 2 electrons in the first shell. In the second and preceding shells, it can hold 8 electrons. So what atoms naturally want to do is, in order to become stable, they want to fill their outer shells. So an electron's charge is -1, okay? And when we're looking at their mass, okay, their mass is super light. So it's so light that we don't actually even calculate this in the atomic mass. I think it's like 1/5230th or something, the atomic mass of a proton. So if you look at a model of an atom, right? Flying around the outside, these orange negative structures are the electrons of the atom, right? Those are the ones that are responsible for bonding. Now, on the inner portion right here, the combination of the molecules, that is our nucleus, right? That is where most of the mass is contained within the cell. Now, within the nucleus, we have these different parts. We have positive protons, and the number of protons in the nucleus is actually what distinguishes what atom they are. Okay. So protons in the nucleus determine the atomic number. Okay. And these purple ones right here that have no charge, those are our neutrons. They have no charge, but they do contain the mass within the object. So inside of an atom, they usually have an equal amount of protons, which are positive, and electrons, which are negative. So therefore, all atoms are electrically neutral, meaning they have no charge. So the positive charge of the protons and the negative charge of the electrons, they cancel each other out, which gives us our neutral atom. Now, when we're looking at a periodic table, the number on the periodic table indicates the number of protons. So, for example, boron right here has 5 protons, atomic number of 5. Whereas nickel right here, that has 28 protons inside of the nucleus. So the number of protons in the nucleus designates its atomic number, and that's how we arrange them from one hydrogen all the way down as we increase our atomic number or number of protons by 1. So now we start combining these things together. So chemical elements is a pure substance. And this pure substance is made up entirely of one type of atom. So it could be many of the same atom, but a chemical element is a pure substance that only has one type of atom in it. And that is what we found on the periodic table. So a chemical element is represented by one or two letter symbols. The first letter is always capitalized. The second letter is always lowercase. So, for example, we have, let's just say lithium. Its chemical element is represented by Li, or chlorine, which is represented by Cl, or carbon, which is just C, fluorine, which is just F. So you can see they can be one or two letters. And again, the periodic table is organized by atomic number, and that is how many protons they have. So when two atoms interact, their electron shells overlap. So this is kind of how bonding occurs. So when those electron shells, when they combine together in the air, those shells overlap, okay? And electrons in the outer shell determine the properties of the element. So all of its chemical composition, all of, excuse me, all of how reactive it is, all has to do with the electrons in the outer shell. Now, sometimes there are variations within these elements. Okay. So isotopes, they have the same number of protons, but they have a different number of neutrons, which means they have a different atomic mass. So isotopes are a little bit strange. So isotopes of the same element, meaning they have the same number of protons. So they contain a different number of neutrons. So what that means is they have a different atomic mass. So their mass number is the total number of protons and neutrons that are found in the nucleus. Again, the mass number. So isotope masses, they differ and they are identified by their mass numbers. So when we're looking at isotopes, their isotope of, let's just say, carbon or oxygen is determined by what their atomic mass is. So they are different masses, but their chemical properties are the same. So since they are the same, they react the same and they are mostly the same element. Now, sometimes we can have radioactive isotopes. And radioactive isotopes have a nucleus that are unstable. And because they're unstable, they will break down at a constant rate. So we can use radioactive isotopes for a few things. Date rocks, see how old these ancient structures are, as well as fossils. We can look at different isotopes found in these structures because they were once living things and see how old they are because remember, they break down at a constant rate over time. We can also use radioactive isotopes to treat cancer and even to kill bacteria. And another thing we can use them is as tracers. So if we need to trace or see if there's a blockage, we can use them to follow the movement of substances within an organism. So if we want to know where the water goes, we can put a tracer in the water and trace to see where that goes within a plant. So if we kind of take a look here at the isotopes of carbon, right? So remember, we have three isotopes designated by their atomic masses. So it's indicating they have a different number of neutrons. So for example, carbon 12 has 6 protons and 6 neutrons, giving us an atomic mass of 12. Now notice they all have 6 protons, carbon 12, carbon 13, and carbon 14, and they all have 6 electrons, indicating that they have a neutral charge. Where they are different is the number of neutrons, which gives us our different atomic mass. So we have 6 protons and 6 neutrons, giving us atomic number of 12, which is why we have carbon 12, which is non-radioactive. Now, if we add another neutron into the nucleus, our atomic, not number, sorry, our atomic mass is going to increase by 1 to 13. That's non-radioactive, radioactive as well. And then finally, if you add another neutron, you get a mass number of 14. So again, isotopes have a different number of neutrons. Now, where we can use some of these radioactive isotopes is in imagery. So radioactive imaging of the thyroid. So the thyroid is this gland that's found in our neck. So the radioactive scan reveals the location of the thyroid glands at the base of the neck. So what we did is we put iodine, okay, and we included the radioactive isotope iodine 131. And the thyroid will absorb that iodine so we can see how those structures are functioning. So when we're looking at our next key question, how are all the isotopes of an element similar? So isotopes of an element share the same number of protons. So remember, protons are what give us our atomic numbers. but the isotopes do have a different number of neutrons, which is why they are isotopes. Spelled nucleus. There you go. So again, what is different about a isotope is the mass number. So the mass number is different because of the different number of neutrons. So let's talk about chemical compounds. So when we're looking at chemical compounds, our first key question is, in what ways does a compound differ from its component elements? In other words, when we combine two elements together, what's different? So a chemical compound is formed by the chemical combination of two or more elements. So again, two or more elements in a definite proportion. In other words, H2O. Water always forms with two hydrogens and one oxygen. And when we make a chemical compound, it's written as a chemical formula. So the chemical formula is water is always H2O, forms in the same proportion. Or salt, NaCl, one sodium to one chlorine. Or carbon dioxide, two oxygens and one carbon, always forms in that same proportion. So in a chemical compound, the physical and the chemical properties of a compound are usually very different from those of the elements from which it is formed. In other words, if you take sodium, which is an explosive metal, and chlorine, which is a deadly gas, and you combine it together, you put it on your food and make table salt. So the physical and chemical properties are much different when they are combined together. So looking at an example here, right? Sodium to the left is a silvery metal. Okay, that is Na. It has one valence electron in its outer shell. And chlorine gas has seven valence electrons. Okay, so this is an example, we'll talk about this a little bit later, of an ionic bond. So what happens is the sodium is going to want to transfer that over. The sodium becomes a positive one, and the chlorine is going to add that electron, and remember, electrons are negative, becomes negative one. So the plus and the minus, they get added together, and we form sodium chloride, which in this case is also our table salt. So again, you can see how the properties are very different from what we start with to what we end with. So let's talk about our next key question here, which what are the main types of chemical bonds? So atoms and compounds are held together by chemical bonds. So when we're looking at chemical bonds, the forces holding these two atoms together, right? These bonds are formed from the electrons, and they're formed by the electrons. More particularly, the electrons that are found in the outer shell of the atom. Okay? So these electrons in the outer shell are called valence electrons. So when you're looking at something, when we're doing bonding, we only really care about the electrons that are found in the outer shell. And those outer shell electrons, depending on how many there are, determines of how reactive something is. So there's two main types of chemical bonds. We have ionic bonds, which is where electrons are transferring from one atom to another, and it creates charged molecules or ions. And then we also have covalent bonds, and covalent bonds are when electrons are shared between the two atoms to form the bond. And we're going to talk about each one of these a little bit more in depth. So ionic bonds are formed when one or more of those electrons are transferred. So they're transferred from one atom to another. Now, what this does is the electrons are a negative particle. So when you gain an electron, you become more negative. When you lose an electron, you become more positive. And think about those two ions as a magnet. The positive is attracted to the negative and they're stuck together. So losing electrons becomes positively charged. So positively charged ions have lost an electron, which is a negative particle, making them have one more proton than electrons. Gaining electron becomes negatively charged. When you gain that electron, you gain another negative ion. So ions, the positive and negative charged atoms, become ions. So again, oppositely charged ions are attracted, almost like a magnet where you have a positive and negative end. And they're attracted to each other and they form an ionic bond. Okay? So let's look at an example of how this works. So again, we have sodium and we have chlorine. But again, remember, we are only looking at the valence electrons. So we really only care about the electrons that are in the outermost shell. So in sodium, we have one valence electron, and in chlorine, we have seven valence electrons. So remember, we want to have a full outer shell for it to be happy. So what happens is that electron from sodium is transferred to chlorine. Now, the outer shell of sodium is filled and the outer shell of chlorine is filled. But what does that do, right? What that does by adding that or losing that electron, sodium becomes more positive. And by gaining the electron in the outer shell, we now have 18, it becomes more negative. And the positive of the sodium and the negative of the chlorine are what are attracted together. So it's the complete transfer of electron that forms charged ions that in turn will make the bonds come together. Now this is different from a covalent bond. In covalent bonds, the atoms share electrons. So they share electrons in order to fulfill their full valence electrons. So they share electrons that move around the nucleus of both atoms, creating a bond. So atoms in a covalent bond can share between 2 and 6 electrons with another element. Okay? Now, molecules are the smallest unit of most compounds that are formed by covalent bonds. So when you make something with a covalent bond, you call it a molecule. It's just a designation of how that bond is forming. So when we're looking at an example of a covalent bond, so in water, each hydrogen atom shares 2 electrons with the oxygen atom. So remember, each hydrogen has one. A hydrogen has one valence electron, and a oxygen has 6, and both of those want to get to 8. So what they do is the hydrogens here, they share an electron with the oxygen. So now that we're sharing that electron with the oxygen, if you draw a circle around the electrons of oxygen, you'll notice that both of their valence are full because the first valence electron only can do 2. So both hydrogens are happy. And in the rest of them, they want to get 8. So there are 8 valence electrons now around the oxygen forming that bond. So you can see how that overlap happens, where they're sharing those electrons between the two molecules. So between ionic and covalent bonds, those are really strong interactions, or really strong bonds. But sometimes we have these really small weak bonds. And these weak interactions, called van der Waals forces, are weak attractions that develop between oppositely charged regions in nearby molecules. So, for example, water is one of these that has these weak bonds. But also, when you think about how do spiders, how do geckos, how do they climb up the wall? So they have all these weak interactions of these nearby molecules that gives them the accumulation to kind of stick to things. So hydrogen bonds are a type of weak interaction as well. And these occur between the hydrogen atom, which I'm just going to distinguish as H, of one molecule of water and an oxygen or nitrogen of a neighboring molecule. So these weak interactions between the slightly positive and slightly negative allow us to have these weak forces that we get. Now, van der Waals forces are really cool, especially in like a gecko. So the underside of a foot of a gecko is covered with these millions of tiny hair-like projections. And you kind of see those looking at right here. Zoomed in a little further, they're almost like little hairs on their fingers. And the projections themselves are made of these fine fibers, creating more surface area to kind of for sticking the surfaces at the molecular level. And then again, allows them to kind of scurry up. So that's an example of van der Waals forces. So looking here, let's kind of review some of the key points that we have. So key question number one, describe the major subatomic particles that make up an atom. So the first one we have are protons. These are positive particles that are found in the nucleus. We also have neutrons, which are neutral or zero charge that are found in the nucleus. And then we have electrons, which are negative that are floating around the outside of the nucleus. Second key question, explain why isotopes of an element have the same chemical properties. The reason is they have the same number of protons and electrons. So since they have the same number of protons, since they have the same number of electrons, their chemical properties are the same. The only thing that is different between them is the number of neutrons. Number three, compare the physical and chemical properties of a compound to those of the elements of which it composes. So, so usually compounds have very different properties. So these very different properties, an example of this would be like water, right? Is made of oxygen, which is a gas, and hydrogen, which is a gas. Combine those together, you get a liquid. Very different properties. And finally, what are the difference between ionic and covalent bonds? So ionic bonds are transferring electrons to form charged ions. Those charged ions then connect. Covalent bonds are sharing electrons to form the bond. So again, ionic are transferring, covalent are sharing. All right, so if you guys are in class or in Mr. O'Brien's class, don't forget they need to answer the critical thinking questions as well as the reading checks that go along with it. But this is lesson number 1 for chapter number 2. And again, the nature of matter. Hopefully this helps you out. And if you have any questions, let me know.